In the last section, we talked about rate laws and finding the rate in terms of the whole reaction, which we call the rate law. So we learned that the rate law consists of rate equals K, and then our reactant concentrations raised, of course, to their order. Today we're going to talk about something called the integrated rate law. And integrated, for those of you who are taking calculus, is where that term comes from, but we'll just pretend the calculus fairy flies over us and does the integrating for us. So we'll just be looking at the results of that in terms of rate laws. And then we'll also look at something called half-life. All right, so first let's look at an integrated first-order reaction. So we know from the beginning of the last lecture that the rate for any particular reactant is equal to the negative change in the concentration of that reactant over time. We also learned that the rate for a reaction can be described as a rate law, where rate equals K, the concentration of the reactant raised to the order. And here we're talking about first order, so we can say that this is a 1. Now, in this particular section, when we're talking about integrated rate laws, we're only going to be talking about the rate law of one reactant reactions. And if there's more than one reactant, we're going to actually create a pseudo reaction where only one reactant really matters in terms of the rate. And when we talk about labs, I can explain that a little more. But we're going to assume in this section that we're just talking about single reactant reactions. So again, we know that rate equals the rate law, and we also know that the rate equals the change in concentration over time. Remember, in the beginning we talked about how these are just two different ways to view the same thing. So they're both equal to the rate. So if the calculus fairy comes along and does what is called an integration of what you see up here, if these two things are equal to each other and we integrate them, we will get this equation that you see below. And it says that the natural log of the concentration at some time, and we can choose any time, minus the natural log of the concentration at the beginning is equal to negative rate constant times time. So this little t here is not involved in the math. It's just telling you what this concentration is referring to. This is the concentration at some time. And this, again, this 0 is not involved in the math. It's just telling you this is the concentration at the beginning. What this allows us to do, and the reason we would want this, is because we can now use this equation to say, okay, if I start with this concentration, fill in the blank, and 50 seconds later, what would be my concentration here? Okay, so this is a very useful equation. This equation is given on your equation sheet, so you don't have to memorize it. But what you do have to know is that this equation only applies to first order reactions. All right, so that is the integrated rate law for first order reactions. We can take that equation and rearrange it into y equals mx plus b form. So we'll leave our natural log of the concentration at some time over here as y, and we're going to move the natural log of the concentration at the beginning over there. That will be our y-intercept. And then we have negative kt as our mx. So negative k, that rate constant, is our slope. And you can tell from this that the slope's going to be negative. And then time is going to be along the x-axis. So here, if it's first order, we can put time along the x, put natural log of the concentration along the y, and plot, and we should get a straight line as long as it is first order. If the reaction is any other order, this equation is not true, and so this graph will not be a straight line. So that is one way that you can figure out if a reaction is first order. If you have a plot in which natural log of your concentration is on the y-axis and time is on the x, if it makes a straight line, then you know it's first order. And if it doesn't, then you know it is not first order. So here you see an example of that. Natural log of the concentration along the y-axis and time along the x. This is a straight line, so I know this is a first order reaction, but again, it is only a first order reaction if it's a straight line. Wherever you cross the y-intercept, which in this case is right here, that is the natural log of your concentration at the beginning. And then your slope is equal to your negative rate constant. All right, so here's an example problem. Using this table and this graph, these are the two pieces of information we have. They want us to find the rate law, the rate constant, and the concentration at a specific time. So if you remember back to when we were doing the table method in the last lesson, we always had more than one experiment in our initial rates. In this type of problem, we're going to have one experiment that we follow over a period of time. So in this experiment, we have time and we have the concentration over that period of time. And then they took and they graphed the natural log of the concentration over that time, and look, it's a straight line. So if we have natural log of the concentration versus time making a straight line, then it must be a first order reaction. Right? So the first thing we need to do is write the rate law. Okay, writing the rate law is simple. It's rate equals K, our reactants raised to their order. Well, we know it's a first order reaction because that plot gave us a straight line. And if we look at our equation, A is the only reactant. So it's the only one in our rate law. So the rate law is simply rate equals K, A, our only reactant, raised to its order. And it's first order because that plot gave us a straight line. All right, now to find K, we're going to use the data at time 0 along with some other time. And we can just randomly pick. But we're going to use our first order integrated rate law equation. Okay, we're going to use this equation. And you can use it rearranged or however you want, but this is the basic equation. And so we're going to take our time and make it 0. Scratch that. Sorry. We take our concentration at time 0. So we don't want to make our time 0. That doesn't work in the math. So we're going to take our concentration at time 0. Our concentration at the beginning was given in the problem as 0.020. So we plug that in for the concentration at time 0. And then we're just going to pick a different time. So that could be any time that you wanted to pick off the chart. Here we picked 50 seconds, or 5 times 10 seconds. And then we need the concentration that goes with whatever time we pick. All right? So let me reiterate. When we're solving for K, we always use the concentration at the beginning right here. Okay, that's the only choice you have. Then for the concentration at time T, if you're trying to solve for K, you can pick any time you'd like to put here, and you put the concentration at that time here. So we plug those in, and this is as simple as hitting buttons on your calculator. So 0.017 natural log, you just hit that button on your calculator, minus 0.020 natural log, hit that button on your calculator, divided by 50, and we get this value for K. Now, notice our units. Up here, we have molarity and molarity, but when we take the natural log of there, there's no units there. And then we have 1 over time, or seconds to the negative 1. This is the rate constant units for first order, right? So if you need to, you can use that table from the previous lesson to remember what your units should be. So if it's first order, then our units are 1 over time. And in this case, our time was in seconds. So there's our rate constant. Now remember, a rate constant is constant as long as you don't change the temperature for that reaction. So we're probably going to use this K in a minute. So once you find K, you can use it in your subsequent calculations. So think free response questions. They're probably going to ask you to find K, and then in the next question, you're probably going to need to use K for something else. So the next question is to find the concentration at 500 seconds. All right, so we're trying to find the concentration at time t. So here's our equation again. This is what we're looking for right here. This is what we don't know, this concentration at time t. We know the concentration at the beginning. We know our time is 500 seconds. They told that to us. And then we know our K value from the last part, from part B. So we can rearrange, move that over there. So now we have the natural log of what we're looking for equals negative KT plus the natural log of the concentration at the beginning. Right? So then we solve from there. The natural log of the concentration at time t, we just put 500 as our subscript to tell that's what the time was. This is not involved in the math right here. Equals negative K, that's from the last part, part B. Notice K has a unit of seconds to the negative 1, and then our time must be in seconds as well, so those can cancel, plus the natural log of the concentration at the beginning. All right, when we solve for that, that's this math right here, then we've got to get rid of a natural log. Okay, to get rid of a natural log, you do e raised to both sides. So when you do e raised to the natural log, that cancels, and you just have your concentration left, and then you do e raised to the other side. So whatever that math is there, we'll plug it in, e raised to the negative value, and here's what the answer turns out to be for that concentration. Now you can check your work on these fairly easily, because the concentration should be less than what you started with, because the concentration that you started with was of A, which is a reactant, and we're assuming that these reactions are moving forward. So we can make sure that this concentration is less than what we started with, and it is less than 0.020. So that is a reasonable response. All right, let's look at another example that involves first-order reactions. We have data from an experiment which examines the change in concentration over time for a first-order, ding, 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 ding. When you read stuff like that, you want to note it. Okay, first-order process at 25 degrees Celsius, and it was used to create the plot below. So look right here, natural log versus time is making a straight line, so it must be first order. Okay, that's an important relationship. But they want to know, okay, what would this look like if we're going at a lower temperature? That's a really good question. So do you think a reaction at a lower temperature would go faster or slower? Faster or slower? I'm thinking that if the temperature was lower, the reaction would go slower, right? So you start out with the same amount. If you're at a lower temperature, it doesn't change your starting amount, but you're going slower. So instead of going down so quickly, your slope is going to be lower in absolute value. Okay? So we're not going to go down as quickly if our temperature is lower. They could also ask you things like, what if the temperature was higher? Well, we'd start at the same place, and we'd go down more steeply. Or what if a catalyst was added? A catalyst speeds things up, right? So we'd start at the same place, but we go down more quickly with a catalyst as well. But if the temperature is lower, we're not going to go down as fast. All right, let's talk about half-life for a second. Half-life is the time it takes for the concentration of a reactant to decrease by half. The time it takes for the concentration of a reactant to decrease by half. So let's say you start with 10 as your concentration. The half-life would be the time it takes to get to 5 as your concentration. So that would be this time, however long that took right there. And then the next half-life would be however long it takes to get to 2.5. And the next half-life would be however long it takes to get to 1.25. Okay, so the time it takes for the concentration to half. is the half-life. Here is an example problem dealing with half-life. So we have a first order reaction, and I know that because the natural log of the concentration versus time is giving me a straight line. They want me to find the half-life for this reaction. And they labeled these values for me kind of nicely. So initially, I have this much natural log of my concentration. And then at 600 seconds, I have this as my natural log of my concentration. So let's see how we can go about finding the half-life, the time it takes for the concentration to half. The first step in finding half-life for this particular example is to find K. So we're dealing with a first order reaction, so we can use the slope of that graph, right? Because the slope of that graph is equal to negative K. And they give us those pretty numbers, so we can use those to find the slope. Change in y over change in x. Okay, we're looking for K. K can help us find the half-life, and K is equal to the negative slope on these straight line graphs. So we're finding the slope. So the change in y, using those values they gave me, over the change in x. So 600 seconds was our time, and then our change in y was 1.02. So our slope, as they calculated it, was negative 1.70 times 10 to the third, and then the units for first order is seconds to the negative 1. Now, that is the slope, but K is equal to the negative slope because K is always positive. So even though the slope's going down, your K value is positive. So there's our K value for this reaction. Right? We're looking for the half-life though. How long does it take this concentration to half? For a first order reaction, there is a shortcut for finding the half-life as long as you know K. And this equation is on your equation sheet, so you always have it. And it says T1/2, which means the half-life, equals 0.693 over K, little k. All right. T1/2 equals 0.693 over little k. So you don't have to memorize this. It's on your equation sheet, but you may want to keep it handy for the homework. So if you can figure out K, which we did in step 1, then you can bypass all this that they're doing over here and find the half-life using this equation. Now this only works for first order reactions, but those are the only ones that they're going to ask you to find the half-life for anyways. So here we know our K value is 1.7 times 10 to the negative third from the previous step where we found K. We can plug that in there and then do T1/2 equals 0.693 divided by that to find T1/2 or our half-life. And in this case, it is 408 seconds. So that means it would take 408 seconds for the concentration of this solution or reaction to half. Now, what we learned from this equation that's probably more important than this calculation is that half-life is inversely proportional to the rate constant. So if the rate constant is small, and this is featured in this box down here, if K is small, then your half-life is going to be really long. So if you have a little rate constant, it means that the rate is slow, and so the time it's going to take for the concentration to half is going to be really long. But if your K value is large, then that means your rate is pretty fast, so your half-life is going to be short. Okay, so they're inversely proportional to each other. And you might want to jot that down or highlight. That's featured in the box at the bottom. Right, so based on what we just said, you should be able to look at these two processes and tell me which one has the shorter half-life and justify your answer. So write your answer in the box on that slide. Which of those two would have the shorter half-life based on what we just said about the rate constant? And then justify your answer.